So, we are back here and we are discussing principal moments of inertia, right. So, principal moments of inertia essentially are the eigen values of this particular tensorial representation of moments of inertia, right. Okay. So, what are the advantages of finding out principal moments of inertia? We will see later, but before that we will just keep it in mind that okay, what do we need to, what is the take back message from this discussion, that the moment of inertia can be represented in this tensorial form, number one. Number two is any tensor in or any real symmetric tensor can be okay. So, there is a theorem which I am or which can be proved mathematically. I am not doing it, but you have to trust me that any real symmetric matrix can be taken into this diagonal form by a suitable similarity transformation, where the diagonal elements are the eigenvalues. Okay. So, similarly, following the same line, because it is a real symmetric tensor, it can also be taken into this diagonal form, where the diagonal elements are the principal moments of inertia, which are the eigenvalues of this inertia tensor. And in this particular frame, if I write this equation, we immediately see that if I have if I have angular velocity in along one of this principal direction, principal coordinates. Okay. So, that along, if I have angular velocity along, let us say the first axis, then we have moment of inertia only along the first axis. We can also write 1, 2, 3 here, right, and similarly for second axis and third axis. So, this is what we learned from this, right. Now, let us deviate slightly from this discussion of vectors and tensors. So, these are the things we need to keep in mind, and also one more thing, this rotational matrix what we have derived here is nothing but the combination of the orthonormal eigenvectors. When we put together the orthonormal eigenvectors, we get lambda 1, lambda 2 and lambda 3. Okay. So, this is not a result which is limited to the discussion of classical mechanics, by the way. This is the similar, in a similar manner we can diagonalize an Hamiltonian in quantum mechanics, right, or any operator in quantum mechanics, for example, right. So, this is a procedure we generally follow. So, any diagonalization of a tensorial quantity in general in a n dimensional space, n could be 3, n could be any higher dimension, we follow the same procedure. And but only thing is, some of the eigenvalue, I mean some of the tensors, whether it is whether it can be brought into a diagonal form or not, that it depends on many other condition. But when we are discussing moments of inertia, and later on we will be discussing small oscillation, there also we will be dealing with real symmetric tensor. If the tensor is real and symmetric, then we are always good, then we can always find a suitable frame of reference where the tensor becomes diagonal. Physically what it means, I will just try to draw a picture and give you an idea. Let us assume we have a cylinder. Okay, let us draw it in a slightly different way. This is our cylinder. Okay. Now, typically what happens is this principal coordinates, especially for moments when we are discussing moments of inertia, which is a property associated with the distribution of mass. Principal moments of inertia in most of the cases are related to the symmetry of the object. Okay. So, let us look at this example. Let us say this is the initial coordinate system we have, x and y and z. Here we are talking about the frame, which is, let us say we have this axis. Okay, so this will not work, just give me a second, this will not work, this will not work. Again, also keep in mind that moment of inertia tensor depends a lot on the origin. If I shift my origin, my moment of inertia tensor will change. So, let us say at the bottom or in the middle I have a point that is the center of this. By symmetry I can always say that this will be the center of mass. I have a axis system which goes through the center of mass, but which is tilted, which is not following the symmetry of this object. Now, if I and it is a cylinder with some uniform density rho. Now, if I calculate the moments of inertia of this particular cylinder in this axis system, I can assure you that I will get all the components I x x, I x y, I z x z, I. Actually, we need not write the lower half itself, because I will tell you why, because it is a real symmetric tensor. So, this half and this half will be identical. So, what we can do is, for real symmetric tensor we can simply write upper half and lower half will be identical to the upper half. Okay. So, we can write essentially 1, 2, 3, 4, 5, 6 elements. Okay. So, 6 elements is sufficient, we do not have to write all 9. Now, if I start rotating this coordinate system, now what happens is, moment we start rotating the coordinate system, every time we are deviating, let us say slightly, or we do not have to be slightly, let us say I go to a coordinate system which is this. So, this is my new x, this is my new y, and this is my new z. Okay. So, what will happen? This tensor, the values will be changing, definitely. These values will be changing for sure, because every time we are moving this coordinate, keeping this point intact, that is a very important thing you have to keep in mind. This point should not change. I am just rotating this by some angle theta, right. This will change. Now, finally, if I go to a coordinate system where the z runs along the axis of the cylinder, and I have an x in this direction and y in that direction. What will happen? Just by the symmetry of this problem, I can tell you that in this particular, this blue frame of reference, this tensor will take this particular form. Okay. So, I 3 will be I z in this case, and also I can tell you something, because it is a uniform, the density is uniform and it is a proper cylinder, this 2 will be I 1 and I 1. So, I 1 and I 2 will be equal. So, I am not writing I 2 here, because I 1 and I 2 will be equal, we can just call it I x and I x, or what is more convenient is we just call it I 1 and I 2. Okay. This I can just I can tell you just by looking at the symmetry of the system. If I take a bottle, for example, which has a cylindrical symmetry, I can immediately tell you that if I take an axis which runs where the z, if I take an axis system where the z axis runs through the axis of this bottle, that will be one axis of symmetry, and I can choose x and y arbitrarily, because we have spherical cylindrical symmetry in this direction. Does not matter where I choose it, I just need two perpendicular axes, okay, and one z axis that runs along the bottle, that will be the symmetric axis. So, typically for moment of inertia, because it is a property which is strongly dependent on the mass distribution of the system, the symmetry, the geometrical symmetry axes are the principal moments of inertia axis. Okay. But typically that might not be the case. Okay. We can have for example, I gave you the example of resistivity tensor. Okay. Resistivity tensor of this so called imaginary metallic block. Now, if it is a proper like crystalline cut, what I mean is, if I take a piece of material and start cutting it by the cleavage planes are the planes which follows the crystalline symmetry, then the real x axis, the physical x axis might coincide with the x axis where which is also an axis of symmetry, and then I might have for some physical property I might have that x axis as a principal axis. Okay. But typically when I am talking about physical other physical properties than moment of inertia, then we might not have a geometrical symmetry axis and a principal axis coinciding. But for moments of inertia, because it is a physical property which depends strongly on mass distribution and mass distribution alone. So, it for uniform bodies, typically the symmetry axis is the principal axis, right. Now, we can also classify systems depending on the symmetry of it. As I said, okay, we do not need this anymore. As I said, we can always have systems, we can always diagonalize the moments of inertia tensor, always. There will be definitely some orientation along which the moment of inertia has to be diagonal. So, we can always find I1 and I2 and I3 for any object. But please again keep in mind that moment we change the origin, your I1, I2, I3 will also be changing, right. Even here, if I am shifting my origin from here to here or some arbitrary position even along this axis, okay, my I1, I2, I1 and I2, these values might change, not might, definitely it will change, it has to change, right. So, whenever we are talking about principal axis, we have to have a fixed point along which is a fixed point. So, the rigid body is rotating keeping one fixed point in it, and that fixed point is our origin all the time, please keep that in mind. Now, for a system, if we have I1 equal to I2 equal to I3, then we call it a spherical top, spherical top. That typically happens for sphere, only sphere, or some system which has this very strong physical symmetry. For example, cube. Cube is also a system. If I take a cube, uniform cube has to be uniform, okay. And if I set my x, y, z such that it is exactly in the middle of the sphere. So, all three moments of principal moments of inertia, just by observing the symmetry of the system, I can tell you if I set the origin at the center, that means origin is my fixed, the center of it is at the fixed point along which it is rotating, then and my, so sorry, actually the x axis has to run exactly through this corner, okay. If that happens, no, sorry, not this corner, okay. So, it might, yeah, it has to run exactly through the middle of this face, similarly y axis middle of this face, okay. So, in that case this will happen. So, this is also an example of spherical top, okay, only if it is a extremely symmetric object, okay. Second example is I1 is equal to I2 not equal to I3, then it's, which is an example we are dealing with here, which is a cylinder, uniform cylinder, where the fixed point is anywhere on this axis, okay. It could be here, of course, changing this fixed point will give you different values of I1 and I2 and I1 and I3, I1 and I2 are exactly equal, but the just by following the symmetry of the object, I can tell you does not matter if we are staying at this point on the axis or that point, we will definitely have I1 equal to I2, which is different from I1 equal to I2, which will be different from I3. So, this set of systems is called the symmetric top. And if I have a system which is very irregular in shape, where I1 is not equal to I3 not equal to I3, we call it an asymmetric top. Okay. Symmetric top, spherical top, symmetric top and asymmetric top. So, motion of this we will be discussing shortly. Asymmetric top actually not much to discuss. Symmetric top, spherical top also it is too easy to understand the motion, everywhere it is symmetric anyway. This is the portion, this is the topic symmetric top, on which we have to spend a considerable amount of time. There will be two types of motion discussed, one is torque free motion, one is with torque motion. So, there will be long calculations in this chapter or this particular topic. So, be prepared for it. Before we go into all this, we need to quickly discuss few other things. One is the theorems. One is the parallel axis theorem, and next will be parallel axis theorem. Let us assume we have this arbitrary rigid body, and let us say we have one axis of rotation given by some direction n running through this, this is with this origin, right, O. And let us assume this is the center of mass of this system, right. And let us assume that another axis which is exactly parallel to n, parallel to this axis, also runs through the center of mass. Now, we want to see, is there any relation between the moments of inertia calculated around this axis and that axis. For that, let us take one point which has a position vector r I and r I prime, right, and this is r. This construction looks familiar, right. We did that when we discussed we generally discuss the motion of a system of particles. So, r I is equal to r plus r I. So, I, which is the moment of inertia measured around this axis, which will be given by sum over I. Again, I am not writing the sum because we are following Einstein summation convention. D I is the distance, right, which is r I cross n square, right. Breaking it into this by putting r I equal to this. So, it will be r plus r I prime cross n capped m I r cross n capped. Now, r cross n capped will be the distance d between this axis and center of mass, right. So, I am just substituting, okay, sorry, there will be a square here, right. So, my first term will be r cross n capped square, which will be capital D square, sorry, small d square, and second term will be m I r, okay. This one will be the distance. So, second term will be r I prime cross n whole square, which will be the distance of this particular mass from this axis which goes through center of mass. So, let us call it d I prime. So, this will be simply d I right, d I prime square, and there will be an additional term which will be 2. So, it will be 2 r, right, m I r cross n into dot r I prime cross n, right. So, there will be 3 terms. Now, what we are going to do is, once again we are simply take this m I inside. I think you all understand by now what we are going to do, and this term is again what, m I r I dashed, which is r I prime, which is the moment measured about center of mass and for a system of particle we have already shown that this moment uniformly vanishes. So, the third term will not contribute anything. Okay. So, third term is equal to 0. So, I will be, and again what is the second term? Second term is the moment of inertia measured around this particular axis which is going through center of mass, right. So, what we can do is we can simply call it I C, okay. Center of moment of inertia measured around an axis, around a parallel axis which goes through center of mass, plus what is this sum of, there is a, okay, there is a sum over I implemented on the whole thing. Now, sum over I means it is the total mass. So, it will be m d square, right. So, that gives us the so called parallel axis theorem, which says I about any arbitrary axis is the moment of inertia about any arbitrary axis is a combination of moment of inertia measured through an axis which is parallel to that axis, but going through center of mass, plus the mass times distance square between that these two sets of axes, basically the perpendicular distance between these two axes, right. So, this is our theorem, which is, and now we move to the next theorem. We have to remove this part here. Next theorem is the perpendicular axis theorem. Okay. Perpendicular axis theorem says what? Let us say we have a laminar object which is lying in the x and y plane, okay. And so we can measure the moment of inertia around x axis, around y axis and around z axis. Then we can write I z z, which is the moment of inertia measured around z axis, which will be I x x plus I y y. I am not proving it, it is so simple, you can find it in any textbook, you can also do it yourself. Please remember, just remember that the mass is in the x y plane, there is no mass distribution along the z axis. Just put that into this I mean write an expression for I x x and I y y, put it into, I mean sum it up, and then you will immediately get I z z. So, I am not proving it for you. Now, coming back to this parallel axis theorem, using this, if I go back to our earlier example of a cylinder, let us assume that we have this cylinder and this is the axis of the cylinder, okay. And let us assume that initially the height of the cylinder is, let us say h. Initially we have an axis system where it is exactly in the middle. So, it is at a distance h by 2 from the top or the bottom, okay. So, this is my x and y and z. So, let us assume in this particular construction I have I1 and let us call it I3 just to clarify, I mean just to make it distinct. So, I1 and I1 are the moments of inertia around x and y, and I3 is along z. Now, let us assume, and also please remember that by symmetry of the problem, this is also the center of mass of the system, because it is a symmetric system with uniform density rho. The middle point of the axis has to be the center of mass, right. So, now if I shift my axis system down here, so let us say, so this is my new set of y and x axis, z axis remains the same. Can we use the parallel axis theorem to check what will be the new sets of moment of inertia around, I mean of course, it will give us the principal moment of inertia, because we are still staying on this axis. What will be the new values of I1 and I3? Of course, we can do that. Okay. So, the shift is by h by 2, right. Now, if I try to calculate it for I1, okay. So, I1 initially it was I1, please understand that initial I1 is this IC for x axis. Okay. So, I1 prime, let us call this I1 prime, let us call this the primed axis. Please do not confuse it with the previous prime notation we have used. I am just taking a specific example. So, I1 prime is equal to I1 plus m, let us say m be the mass, m h by 2 whole square. So, I1 prime will be I1 plus m h square by 4. Similarly, I2 prime will be I2 plus m h square by 4. Okay. I2 which will be equal to I1 prime, and I3, what will happen to I3? See, we have not shifted along the z, I mean sorry, the shifting is along z. So, there is, so we have kept ourselves on the same z axis, z has not shifted. So, I3 prime will be equal to I3. So, we have shifts in the first two components, or the x and y component, iz component remains unaltered. So, this is a result we might use later on. Now, we will end the class with a very small problem. The first problem of this problem set, we have many actually, I have just kept it for till the end, so that we can finish it all together. So, we have a rigid body, once again this is a familiar rigid body, we have 3 particles at 3 different positions. We have to find out the moment of inertia about an axis which is going through center of mass and perpendicular to the plane of the body. Now, once again I am not solving it for you, but I will give you a sufficient hint so that you can do it. Now, let us say these 3 are the mass points. Okay. So, we can always form a triangle through these 3 masses, and by symmetry of this problem, the center of mass, see frankly I do not recall what was the values we have determined for center of mass, but you can find it out once again, it is very easy. The center of mass will be somewhere on this plane by the symmetry of the problem. Now, we have to find out the moment of inertia about an axis which is perpendicular to this plane of the triangle and going through center of mass. Ideally, we have to find out the equation of, or we have to find out this vector direction and have to take all the distance from this vector by using d I is equal to r I cross n capped, but in this case this is not necessary, because we already have a point which will be falling on this axis, and also it is in this plane which is the center of mass. So, what we can do is, once we know the coordinate of the center of mass which we calculated in the previous class, we can just take mutual distance of these 2 points, and we know that mutual distance between any 2 points d is given by root over x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square. So, similarly, what we can do is we can calculate d1 for d1 and d2 and d3 between these 3 points, and we can compute I to be equal to sum over I mi di square. So, you can finish it yourself, it is one way of looking at it. Now, that was easy, because we already specified that the axis is going through center of mass. Let us assume if I give you any arbitrary axis to work with, which is not even going through center of mass, or let us say I give you an axis which is going through the origin in some arbitrary direction, then we just have to follow this construction. Okay. We have to construct an unit vector which is, if I give you a direction, that means I am giving you the unit vector, or if I am giving you a vector direction, you just have to divide it by the magnitude and you get an unit vector, and from this you just calculate the mutual distances of 3 points. Does not matter if it is falling inside the rigid body or outside, it does not matter really, moment of inertia can be calculated, and then you have to just in that case this will be your d1, d2 and d3, and then you go back and put your values in this formula and you get a value of moment of inertia. So, we can always do that. Right. So, we end here, and next class we will do some problems, and also we will go forward in terms of in the discussion of principal moments of inertia. We will define something called ellipsoid of inertia, and then we will move on to Euler's equations. Thank you.